Alright, my name is David Arnold, and I'm working with Jesse Gibbs and Dalton Parrish, and our senior design project is the miniature hydroelectric generator, an economical solution to rural power shortages. As an introduction, rural communities, especially in third world countries, do not have access to electricity like those in first world nations. Some individuals living in the United States do not have access to municipal amenities while residing in rural locations and thus do not have an abundant supply of electricity. Additionally, countries such as the United States are becoming more weary of producing electricity by means of coal-fired power plants and are considering alternative methods that are considerably more environmentally friendly. With a growing global population, more power is being consumed annually and new methods of power production are desired. Within the report, I put a diagram of, a graph with the amount of electricity being consumed since 1800, and it's an exponential increase. I also found that states such as California are phasing out gas-powered cars and such, and we're trying to become more economically and environmentally friendly with our electricity production. These are the parts that were used in the electric generator. There's a 10-watt turbine generator, a DC-DC converter, both purchased off of Amazon. We were able to obtain a brass adapter from Home Depot, and then the wire connectors and shrink sleeves came from Lowe's. So the total cost was only $41.76, which is not an extraordinary amount. Specifications are all listed here with the output voltage and current, the resistance between the wires, the insulation resistance, the maximum pressure with the outlet closed, the maximum pressure with the outlet open, the starting pressure, the mechanical noise, the generator life, and the working temperature range. The maximum pressure when the outlet's closed should never be a factor because we don't have any valves or anything around the exit. But the starting pressure is important. That 0.05 megapascals roughly is equivalent to about 7 psi. So you don't have to have very much running water. Whenever we ran it in the spigot, you don't have to turn the spigot all the way open to get electricity to be produced to charge a smartphone. The mechanical noise is very, very low. You can barely hear it running. And impressively, the manufacturer's life is greater than or equal to about 3,000 hours. The temperature range is adequate for temperamental environments. So obviously this probably would be a great place to use in Death Valley or Antarctica. The engineering design. The design of the hydroelectric generator has been around for the better part of 100 years, but more recent designs are much more refined. The turbine generator system can be scaled up and down as much as desired for the applications. Our report focuses on small-scale applications. Numerous miniature generators could be linked to the same water source for more power or battery charging capabilities. So basically, we have huge hydroelectric dams that can put out many megawatts of electricity, and then we have generators such as ours that are only putting out 220 milliamps of electricity. So if you were to run a bunch of these generators to the same water source, ultimately what you do is you'd be producing a lot more electricity, or you could charge a battery a lot quicker. For the implementation of the hydroelectric generators can be used in off-grid situations to power small electronics. The generator can also be used in plumbing that has high enough pressure to turn the turbine. This would take advantage of the resource that is already there. It can be also used in third world countries with water sources such as streams, creeks, rivers, etc. I mean, it doesn't have to be in a third world country. You could do it in this country too with running water. As far as the plumbing used in homes, if you were to wash your car, for example, you could take another adapter like we have and then hook a hose up to it, and you could charge your phone or something while you're washing your car. If you put it in between the shower head and the water, you could charge something while you're taking a shower. And you could also run it to like your gutter. So if there's a rainstorm, you could have just the gravitational energy of the water running down the gutter to run it. So I mean, the possibilities are endless as far as implementing this device.
Hello, my name is Dalton Parrish, and I will be going over some of the calculations we used in our senior design report. This first part is a drawing of the wheel. I use that to calculate the length of the teeth here, because it was pretty hard to calculate the caliber. Next, this is the cross-sectional area of the faucet where the water goes through. I calculated what percent of that the wheel covers. Next, this is the experiment we did. We filled a 5-gallon bucket using an outdoor water faucet and converted that to a volumetric flow rate, and then divided that by the cross-sectional area to get the speed at which the water flows through. Next, these are some calculations to get the rotational speed. So you just take the tangential speed, and then you times it by the circumference, and then times by 2 pi to get the radians per second. After that, to calculate the power, or calculate the torque, we took the 10-watt motor and then divided that by the radians per second, and that gives us a value of 1.89 Newton meters. Divide that by, I guess, the radius of the wheel to get 108 Newton force. And then to calculate the pressure, just did force over area, and that gave us 474,000 pascals, which that's a pretty good value because that's close to what typical water pressure would be in a house. Okay, after that we had all the values to calculate Bernoulli's equation, so we just had to find the velocity, or velocity 2, which is the velocity coming out of the hydroelectric generator, that to be 1.27, which that's higher than in the pipe because obviously when the pressure drops, the velocity must increase. It's just a conservation of energy. And speaking of that, we when you derive Bernoulli's equation, you get Euler's equation, which is work equals the difference in power over the density. So I calculate that here to get 79 watts. And then just 10 over 79 is 0.13, and that's the efficiency of the hydroelectric generator. Thank you.
So my name is Jesse Gibbs, and I'm going to talk about troubleshooting. We used an LED to determine if the generator was putting out current. It did light up the LED, and we also blew through it with our mouths, air pressure through, and it would light up the bulb. The harder you blew, the brighter the bulb would get. Also, the original USB cable did not work, so the cable has 4 wires in it, and 2 of which are data wires. They go back from the phone to whatever it's plugged into to give that data from the phone, and apparently it doesn't work without that data being transported, so we had to get a different USB cable that didn't have data wires. The DC motor constrained within 2 O-rings, and they're already greased from the factory, so no maintenance there. And all the wires we used were insulated, so once you set it up, everything is ready to go and no maintenance. So in conclusion, the application for the hydroelectric generators are endless. It could be positioned between a shower head and a nozzle for intermediate electricity while one showers, in between a garden hose and a spigot for one washes their car or waters the grass, or even at the base of the gutters for at large rainstorms. Water could be rerouted from a stream for consistent and steady power for ready use in the DC batteries or LED lighting for small homes. Due to low cost of the system and the zero maintenance lifetime of the generator, those without high mechanical incline can set up this anywhere. Water is abundantly present, and that's the conclusion.
Water's on. Turbine spinning with
charging symbol.